Malaysia Green Building Council, also known as Malaysia GBC, is an organization that promotes green building programs, technologies, and design practices, aims to make Malaysia an eco-friendly and sustainability place on Earth. Malaysia GBC was founded in May 2009 by a group of passionate building consultants, academia, and representatives. Even since Malaysia's building has increased, the efficiency of resources used in each building was built with green in mind. Malaysia GBC is also supported and associated with most of the top industry institutions. In the year 2015, Malaysia GBC became an established member of the World Green Building Council and known to be the only organization in Malaysia to be supported by the World GBC. Malaysia GBC continues to be the platform that networks, promotes, educates, and most importantly, develops the sustainable, built into the land of Malaysia. With much more passionate industry professionals, we can make Malaysia a greener and better place on Earth.
Good morning, everyone. Ladies and gentlemen, it is my honor to be the moderator for this session. I'm Regine Chu, the Council Member of Malaysia Green Building Council and also the Chair for Northern Chapter. Malaysia GBC is a non-profit organization that promotes green building and sustainability. We're looking for more green-minded industrial players like you to join us to grow the green economy. Please feel free to type in the questions that you would like to ask the speakers, and we'd like to address all the questions during the Q&A session. Our presentation is about to begin. Our esteemed speakers today, Ms. Selina Chin, distinguished guests, ladies and gentlemen, good morning. First of all, on behalf of Malaysia Green Building Council, I would like to welcome all of you to this webinar. Today, we'd like to have presentation from Samuel Yamamura. Before the presentation begins, allow us to introduce the speaker, Ms. Selina Chin. She is the Specification Manager of Samuel Yamamura Woven Products Central Berhad. She has 13 years of experience and exposure in building material industry. Prior to this, she was attached to Terra Malaysia, Central Berhad. During her career, she was specializing in thermal insulation industry. She has vast experience and exposure in dealing with not only the local thermal insulation industry players, but also international market, such as Samuel Yamamura Woven Products business span across the globe, has strong presence in major Asian countries such as Australia, North America, South Africa, etc. Without further ado, I would like to welcome the speaker to deliver the presentation. The title of the webinar today, Field Evaluation of Radiant Barrier in Hot and Humid Climate Conditions. Over to you, Ms. Selina Chin. The floor is yours now.
Thanks, Regine. Good morning, ladies and gentlemen. Thanks to MGBC for having Samuel today to share on the projects on title Field Evaluations on Radiant Barrier in Hot and Humid Conditions. This will be the contents for today. First, let me introduce a little bit on Malaysia's weather, then the background of the study, what are the problems that we face when coming to calculate RSI, the objective of the field test, what are the methods used to calculate the RSI, and what are the results of the field test. After we understand how radiant barrier performs, how do we select the correct material for a specific roofing system, followed by installation guide. Let's begin. Malaysia is located near equator with hot and humid climates. average temperature of 27.5 degrees Celsius, annual average daily solar irradiance up to 5.56 kilowatt hour per meter square. The major contributor to heat gain actually is the sun. Sun will heat up the roof then will transfer the heat into the building through conductions, convections, and radiations. According to a research done by NAHA in 2003, 50% of the thermal building loads in hot climates come through the roof. And according to the research done by Richard in 1977, the proportion of heat transfer that flow down from the roof through ceiling are 87% are from radiations, 30% are from conductions and convections, whereas heat transfer through walls are 70% from radiations, 25% from convections, and 5% from conductions. Now we have understand that 50% of the thermal load actually is coming from the roof. Is that really help when we insulate the roof with radiant barrier? Let's find out. These are the types of thermal insulation technology used for building energy efficiency. It divided into 4 types of technology. First is bulk technology, reflective technology, nanotechnology, and vacuum technology. Bulk technology include fiberglass, mineral wool, expanded polystyrene, extruded polystyrene. Radiant barrier, reflective insulation, interior radiations control coating, and gas fill panels are the example for reflective insulations. Whereas for nanotechnology, one of the example is aerogel, and vacuum technology includes vacuum insulations panel. Today, we will focus only on radiant barrier and reflective insulations. What is radiant barrier? Radiant barrier consists of 2 or 1 high reflective material, usually is aluminum foil, laminated to a substrate. The substrate can be woven fabric, bubble fabric, paper fabric, or foam, or etc. Aluminum foil can reflect 95% of the heat. How do you express the thermal performance? The thermal performance is expressed in thermal resistance in SI unit. SI unit is an international system of unit and is denoted as RSI. What are the factors that affecting this RSI? First is the emissivity of all surface that facing the enclosed airspace. Second is the airspace dimension in the directions of heat flow. Third is the heat flow directions, whether it's up or down. And fourth is temperature different across the airspace, or we call it boundary temperatures. There are 3 types of testing method to measure the thermal resistance of radiant barrier and reflective insulation in the assembly. There are laboratory testing, calculation method, and field tests. Let's explore each testing together. Heat flow meter is one of the example of lab tests. It's tested according to ISO 8301 or STM C518. What is the advantages of using this heat flow meter? First is measure the steady state of one-dimensional heat flow through the sample. It can calculate the sample thermal conductivity and resistivity. This method is very sensitive. You can measure the thermal resistance of 0.1 meter square Kelvin per watt and can measure heat flow up, down with different angle. And it's very easy to operate and can obtain the total RSI of the assembly. The disadvantages are specimen size are limited by the equipment chamber dimension and is very sensitive to heat loss through the sample edges and must be calibrated using a non-thermal resistant material. This is one of our project, which is an MRT project that tested under this method. The insulation component consists of 8 mm of bubble foil with 75 mm of airspace and 50 mm of mass insulation. We sent this assembly to UKM and tested under heat flow meter methods. And the total RSI we got is 3.05. And this report actually is generated by UKM. Another example of lab test is guarded hot plate. It's tested according to ISO 8302 or STM C177. The good point by using guarded hot plate are it measures steady state heat transfer through flat surface only. It's absolute matter because need to measure the specimen dimensions, temperature, and electrical power on it. And it can operate over a wide range of temperature. The negative point are because it's just for the flat specimen only and with limited specimen size. It must have a good contact between the specimen and the hot plate because some of the sample may have uneven surface. Temperature imbalance between the hot plate and the guarded housing must be controlled. The last example of lab test is guarded or calibrated hot box. It's tested according to ISO 8990 or STMC 1363. The advantages of using guarded hot box are it measures steady state heat transfer through a specimen, is suitable for homogeneous and non-homogeneous sample. It can be rotated to simulate the actual specimen orientation in the field. The specimen size is definitely bigger compared to the previous two methods, and more thermocouple are used for better temperature measurement accuracy, and it can evaluate the U value for building assembly. The disadvantages for this method are the result may be affected by the air movement in the metering chamber. It takes longer time to reach steady state. The box must be sealed to prevent air infiltrations and lack precision because of heat loss corrections is needed. Second testing method is calculation method. It is according to ISO 6946, Australian and New Zealand 4859.1 and STM STP 1116 standard. It is a mathematical models to predict the thermal performance of radiant barrier and reflective insulations assembly. You can get the result very fast, but the result may be different for field measurements evaluations. This is the example of using calculation method. You just plug in the number into the software, then you can get the total R value. Field test is the method that is more complex, more time consuming, and require more resources because the building are studied under actual weather conditions. It provides you the data that is most accurately represent the conditions in which the building are exposed to, but there are many complications arises in the fact that under actual weather conditions, the climate variables are uncontrollable. Today, we'll focus on field tests. These are the problem or the reason that trigger us conduct this field test. There are lack of field study on the performance of radiant barriers in hot and humid climates. Not much scientific data on the influence of commonly used roofing material, for example, tile roof or metal roof, on the performance of radiant barrier in hot and humid climates. There are ongoing debates on the performance of radiant barrier. For example, people are debating on the efficacies of radiant barrier. The objective of the whole field test is to determine the RSI and attic temperature of roof assembly with and without radiant barrier building material, to evaluate the influence of different dimensions of airspace on RSI and attic temperature of reflective insulation system, and to compare the RSI and attic temperature of mass insulation, radiant barrier with mass insulations, and radiant barrier building material. 3 test cells were built in our factory located in Ayakura, Malacca. Each test cell was equipped with 1 door. Dimension is 2.2 meter width with 2.5 meter length, and the height is 3.3 meter. The distance between these test cells is 1.9 meter. All of the test cells are facing west. The roofs are designed in such a way that the overall configurations can be changed easily because we will test on the performance of different type of tile roof, different type of radiant barrier, and different dimensions of airspace. The wall and the floor are insulated with 100 mm thick wool with 80 kg per meter cube. This is to minimize heat gain and heat loss because we just want to measure the heat from the top to bottom. These are the equipment used during this test. First is the thermocouple, measure surface temperature. Then the heat flux transducer to measure the heat flux across the attic. Pyranometer to measure solar irradiance. Number 4 is main data logger to capture all the data. and portable data logger to capture attic temperature. This is where the thermocouple located. We have 6 thermocouple below the roof tiles, 3 below the insulation foil, and 3 on top of the ceiling. This is the sectional view of thermocouple locations. Every thermocouple was installed using aluminate adhesive tape. This is the locations of heat flux transducer. It is installed on the ceiling with silicone thermal adhesive to measure the heat flux across the attic. And pyranometer were raised above the roof. This is installed to measure the irradiance from the sun. Data logger was installed in the attic to measure the attic ambient temperature. This is the master project of our evaluations. Total, there are 7 phases. For phase number 1 to phase number 5, we tested under concrete roof tiles with different dimensions of airspace, different type of radiant barrier. And phase number 6 and 7, we tested under metal roof with different insulations and radiant barrier. We will go into details phase by phase later. This is the calculations for overall RSI. For phase number 1 to phase number 5, the overall RSI is the RSI of the attic plus the RSI of the airspace. This is the detailed dimensions of the airspace. Airspace dimension remain unchanged, but we will change the airspace dimension according to the project tested. The overall RSI for phase number 6 and 7, which are using a metal roof, is the total RSI of the attic because there is no airspace on top of the building. This is the dimensions for metal roof. Along the study, along the evaluations, we face a lot of challenges. For example, irregular RSI fluctuations. We get nearly 0 RSI, large RSI, sudden fluctuations in RSI, or high RSI variations or negative RSI. After a thorough study, we found out that this might be the possible causes for irregular RSI fluctuations. Negative RSI can be caused by heat flow upward rather than downward. Large RSI can be due to changing point between the heat flow directions. Nearly 0 RSI is caused by small temperature difference, and sudden fluctuations is affected by cloud shadowing and raining. And high variations can be caused by wind and cloud shadowing as well. Due to all these challenges and irregular RSI fluctuations, we have fixed some selected selections criteria for RSI. First, the data must indicate heat flow down. Second, heat flux must be more or equal than 1 watt per meter square. Temperature difference across an airspace must be more or equal to 0.1 degrees Celsius. Irradiant at least 600 watt per meter square. The average RSI block fluctuations is less than or equals than 25% of the running average RSI. Let's go into phase by phase in detail. Phase 1 is tested under concrete tiles with 25 mm airspace. Test cell 1 is using woven foil, double-sided woven foil. Test cell 2 is without any foil. Test cell 3 is using double-sided aluminum foil. Let's see what is the result. This is the objective for this phase, is to determine the RSI for various types of radiant barrier with 25 mm air gap under one type of roof in hot and humid climates. This is the result for phase 1 for attic ambient temperature. Maximum outdoor temperature is 43.3. And test cell 1 with double-sided aluminum foil achieved 37.2 degrees Celsius. Test cell 2 without any radiant barrier achieved 46.1 degrees Celsius. And test cell 3 with double-sided bubble foil achieved 36.7 degrees Celsius. You can see from here, test cell 2 without any radiant barrier achieved the maximum 46.1 degrees Celsius. In terms of RSI comparison, Test cell without any radiant barrier achieve RSI 0.37, and test cell 1 with double-sided aluminium wound foil achieve RSI 2.37, and test cell 3 with double-sided aluminium bubble achieve RSI 2.93, which is the highest among the three. Phase number 2. We still tested under concrete tiles. We increased the air gap into 50 mm air gap. The product tested are remaining the same. The objective for this phase is to determine the RSI of various types of radiant barrier with 50 mm air gap under one type of roof in hot and humid climates. Outdoor temperature is 37.2 degrees Celsius. Test cell 1 with 25 mm, with double-sided aluminium wound is 38.3 degrees Celsius, and test cell 2 without any radiant barrier is 45.7 degrees Celsius, and test cell 3 with double-sided aluminium foil is 36.6 degrees Celsius. Again, test cell without any insulations have the highest temperature in the attic. Okay, the RSI for test cell without any foil is 0.4. Test cell with double-sided wound foil is 2.19. Test cell with double-sided aluminium bubble foil achieved 2.69 RSI. Let's go to phase number 3. Tested under concrete tiles, we only use one type of product for this phase, and we change the dimensions, airspace dimensions for test cell 1 into 50 mm airspace, test cell 2 25 mm airspace, test cell 3 is 75 mm airspace. The objective for this phase is to evaluate the RSI of radiant barrier based on different air gap. The outdoor temperature is 37.3 degrees Celsius. And test cell 1 with 50 mm airspace achieved 37.3 degrees Celsius, and test cell 2 with 25 mm airspace achieved 38.4 degrees Celsius, and test cell 3 have the lowest temperature, which is 35.8 degrees Celsius. This is 75 mm airspace. In terms of RSI comparison, test cell with 25 mm airspace have RSI 2.15, with 50 mm airspace has RSI 2.31, with 75 mm airspace it has a tremendous increase in the RSI, which is 3.08 RSI. We already come to the middle of the test of the field evaluations. Phase number 4, we tested double-sided aluminium bubble foil, and the dimension for each test cell remain the same. The objective of this phase is to evaluate the RSI of radiant barrier based on different air gap. Outdoor temperature is 36.9 degrees Celsius, and this test cell with 50 mm airspace achieved 36.7 degrees Celsius, attic with 25 mm airspace 37.8 degrees Celsius, and attic with 75 mm airspace 35.4 degrees Celsius, which have the lowest attic temperature. In terms of RSI comparison, RSI for 25 mm airspace have 2.41, and RSI for 50 mm airspace is 2.41 as well. And RSI for 75 mm airspace, again, it increased tremendously in this area, 3.09. Phase number 5, we have changed the roof, 2 of the test cell of the roof to clear tiles with 25 mm airspace. Test cell 1 installed with concrete tiles with double-sided aluminium foil. Test cell 2 clear tiles without any foil. Test cell 3 clear tiles with double-sided aluminium foil. The objective of this phase is to study the performance of clear tiles versus concrete tiles. You can see from the picture, test cell 1 remain concrete tiles. Test cell 2 and 3, we have changed the roof to clay tiles. Outdoor temperature is 37.2 degrees Celsius. Test cell 1, concrete tiles with double-sided aluminium foil achieved 36.7 degrees Celsius. Test cell 2, clay tiles without any radiant barrier, without any foil, achieved the highest temperature, which is 43.8 degrees Celsius. And test cell 3, clay tiles with double-sided aluminium foil achieved 36 degrees Celsius. In terms of RSI comparison, RSI for clay tiles without any foil is 0.4. RSI for clay tiles with double-sided aluminium foil is 2.26. And clay tiles with double-sided aluminium foil is 2.4. From here, you can see clay tiles with radiant barrier perform slightly better compared to concrete tiles with radiant barrier. Phase number 6, we have changed the roof to metal deck. For test cell 1, we are using mesh insulations with woven foil. And test cell 2, we are using 8 mm double-sided aluminium foam foil. And test cell 3 is double-sided aluminium bubble foil. The objective of this phase is to compare the RSI of mesh insulation with radiant barrier against different type of radiant barrier. You can see from here, we have changed the roof to metal roof. Outdoor temperature is 40 degrees Celsius. Test cell with mesh insulations and aluminium foil is 39.2. Test cell with double-sided aluminium 8 mm foam foil achieved 39.5 degrees Celsius, and test cell, achieved 38.7 degrees Celsius. And test cell with bubble foil achieved 39.5 degrees Celsius. In terms of RSI comparison, roof with double-sided aluminium bubble have the lowest RSI 1.77, followed by roof with mesh insulations with double-sided aluminium have RSI 2.37, and the highest is 2.23, and the highest is 2.37, which is using double-sided aluminium foam foil. We have come to the last phase of the project. Using metal deck, for test cell 1, the insulations remain unchanged. For test cell 2, we use mesh insulations only, and test cell 3, we are using bubble foil. Let's look at the results. Okay. The objective for this phase is to study the RSI performance of different type of insulation system under metal roof. This is the attic temperature result. Outdoor temperature is 37.7 degrees Celsius. And metal roof with mesh insulations and aluminium foil achieved 37.6 degrees Celsius. Wool alone only is 39.1 degrees Celsius. And mesh bubble foil itself is 38.1 degrees Celsius. For RSI comparison, wool itself have the lowest RSI, which is 1.61, then followed by bubble foil 2.02, and the highest is wool plus radiant barrier, which is 2.77. In conclusions, we can say that for concrete tiles with configurations of 5 mm space, test cell 1 woven foil with 2.37, without foil is 0.37, bubble foil 2.93. There is an improvement of 24% when you use woven foil, when we change woven foil to bubble foil. Test cell 2, concrete tiles, 50 mm space. There is an increment of 25% in the RSI when you change from woven foil to bubble foil. And comparing concrete tiles with clay tiles, there is a 6.2% increase in the RSI when you change from concrete tiles to clay tiles. In terms of air temperature comparison, for phase 1, concrete tiles with 25 mm, you can see that there is a 0.5 degrees Celsius reductions when you use bubble foil. And for phase number 2, concrete tiles with 50 mm airspace, there is a 1.7 degree of reductions compared woven foil and bubble foil. And for clay tiles and concrete tiles, there is a 0.7 degrees Celsius reductions when you comparing concrete tiles with woven foil and clay tiles with woven foil. For phase 3 and 7, for phase 3 and 4, concrete tiles using woven foil and concrete tiles using bubble foil. For phase 3, it is improved by 43% when you increase the air gap from 25 mm to 75 mm. For phase number 4, it's improved 28% on the RSI when you increase 25 mm airspace to 75 mm airspace. In terms of temperature, there is a reduction of 1 to 1.5 degree with every incremental of 25 mm enclosed reflective airspace. Thermal performance for phase number 6 and 7. As shown here, phase number 6, you can see here foam foil achieved the highest RSI, and phase number 7, it shows that mesh insulations work better together with mesh insulations compared to mesh insulations alone. In terms of attic temperature comparison, foam foil have the lowest temperature, which is 38.7 degrees Celsius, and foam foil and mesh insulations with radiant barrier have the lowest temperature, which is 37.6 degrees Celsius. We actually published these field evaluations in all these conference. In 2016, we are published in IREM conference, an international conference on energy and environment and economic, and roofing technology conference in China. In 2017, we published in International Research Conference on the Sustainable Energy and Engineering Material and Environment, and the International Conference on Environment on Energy Engineering Conference. And the last one is Metal Roof Conference. If you guys are interested in these publications, to drop me an email that I will send the details to you. After we understand how radiant barrier works, how radiant performs, the selections of suitable radiant barrier to maximize building thermal insulation's performance is very important. There are two important selection criteria, whether it's single-sided foil or double-sided foil. If you go for double-sided, whether it's double-sided aluminium or one-side aluminium, one-side metallized. Single-sided foil actually is suitable for one reflective airspace. Normally you saw metal roof system where there is only one side of air gap available. Example, as this diagram shows, metal roof with bulk insulations and radiant barrier, this is only have one reflective airspace. Double-sided aluminium foil, aluminium and metallized actually function as same as single-sided aluminium foil, but aluminium and metallized double-sided foil provide a better vapor barrier. For double-sided aluminium, it's suitable for tile roof system. For example, in tile roof system, there are two types of air gap. One air gap in the attic airspace, another air gap at the batten area. This is when you use double-sided aluminium foil in tile roof system, this can maximize the thermal performance. Of course, a suitable material always come together with a proper installations. There are important guidelines to follow. First, ensure that the high reflective surface is facing the air gap. Ensure no leaking on the roof, otherwise aluminium will be oxidized. We encourage 3 to 6 inches overlapping at the edge and avoid installations during raining day. This is how the installation looks like when you are using paper type of foil. Paper foil itself is very moisture sensitive and do not provide any strength. The installation for paper foil have to come together with wire netting to support the whole system. If you go for woven type of aluminium foil, Then the installation, you can ignore the wire netting because woven itself gives you a better strength compared to paper. This is one of the systems that we purposely created to achieve certain R value. For example, you can look at here, metal deck with mesh insulations, then radiant barrier and reflective airspace. We purposely create this reflecting airspace so that the overall R value will be increased. This is the installations for bubble foil and foam foil. Due to the product texture itself, because the product carry weight, during the installation, it will sag a little bit. So we'll see a sagging at here. This sagging actually create an enclosed airspace, which is good for RSI. Okay. And this is another system that created to achieve certain RSI. You can see here there is 2 reflective airspace here. Definitely the RSI will increase tremendously. That's all from my sharing. I hope it's benefit to you. I will pass it back to Eugene.
Thank you, Selina. Thank you. So, yeah, for the very informative, a lot of numbers here for the sharing in this morning. Yeah, we are living in the tropical weather, and knowing how design like this can actually reduce the temperature and reduce the cooling load is very important. Yeah. So, all right, ladies and gentlemen, now we have come to the question and answer session. We will take the questions that we received from the floor. Yeah. Any questions? Yes, I'm seeing questions coming in. Yeah. All right. Okay. So, question 1. Yeah. Can you elaborate further on the location of this airspace for the benefit of many on where exactly the airspace is measured at the roof? Yeah. Selina? Yeah. Sorry, Selina, you might have to unmute again to answer the question. Are you going back to the slide, right? Yeah.
Hello, Eugene. Hello, Regine.
Yeah, yes.
Can you hear me?
Yeah.
Can you see my slide?
Here. Yes. Okay. Can you please elaborate further the question from this question, the question from the audience? Yeah. The location of the airspace. Yeah.
Okay, the location of the airspace actually is the batten height airspace. Just now we have shown we tested on 25 mm batten height. There's the batten height here. So the foil is below the batten and the tiles is on top of the batten. So there's an airspace here. We change from 25 mm to 50 mm or consider as a counter batten. Then we increase the airspace here to 75 mm airspace.
And this particularly refer to the concrete tiles, right? Yeah.
Yes, concrete tiles or clay tiles.
Yeah. Okay. So let me move to the second questions. Any test has been conducted to compare steel decking, I think it's referring to metal roof, with polystyrene foam below the concrete roof tiles and clay roof tiles?
Unfortunately, no. Yeah,
I think it's referring to the PU foam, is it? I get it.
Maybe the polystyrene foam. Yeah.
Yeah. Okay.
If the audience is interested to conduct this test, maybe you can send the inquiry to us. We will look at it whether we have this opportunity to work together to conduct this research.
That's a good idea, Selina. Yeah. So, okay. Question 3. Let's move for the third question. Heat transmission across the roof or attic space to underside of the ceiling is mediated by radiation, conduction, and convection. This is a statement, yeah. The rationale of radiant barrier is principally reduce heat transfer from reduced radiation. Radiation may dominate, sorry, I need to go back. This is a long question. May dominate if the convection has low factor due to perhaps confined attic. However, if roof space is vented, then convection may well dominate heat transfer across roof space. Your study is not rigorous, IMO is not rigorous enough. No attempt at a theoretical analysis. Effects of conduction, convection across roof space. Number 3, a study which only consider radiation without looking at the other two factors may be really subjective. What do you think about this statement, Selina? I think it's because for this is only addressing the radiation. What about the other two factors? Yeah.
Yeah, I agree with you for our this field evaluations, because the main heat actually is coming from transfer through radiations. So for these evaluations, we are tested on radiation heat only. So we have not taken into considerations of the conductions and convections. But I do agree, attic with ventilated attic actually perform better, have higher R value compared to a non-ventilated attic.
Mm-hmm. Okay, yeah, because of the air movement, right? Yeah.
Yep.
Okay. So, okay, now we go to the question 4, yeah? Okay, and now we have a shorter questions. How to overcome the heat transfer at the purlin area?
You mean by thermal bridging, right? Okay. Actually, in the market, there are one type of thermal stop. So you can purchase a thermal stop to install at the purlin area.
Thermal stop, okay, yeah. So they may also email you or contact you to clarify on this statement, right? Yeah, or to get information on this. Yeah. All right, thank you. Questions, next question. How much is the cost of the radiant barrier, and is it work for sound insulation too?
Okay, the cost of the radiant barrier actually is very economic if you compare to mass insulations. It costs around maybe 7 ringgit per meter square for just a normal type of woven foil. And in terms of sound insulation, it has to work together with mass insulation. If you use a woven foil itself only, actually it doesn't function as sound insulation. It have to work together with mass insulation.
To actually absorb the heat. Yeah.
Absorb the noise. Yeah.
Absorb the noise, right? Yeah.
Yes.
Okay. So now we move to the next question. Yeah. So what is the lifespan of the insulation foil in hot and humid climate, especially in Malaysia? Yeah, I think this is very relevant to us. Very hot and humid in Malaysia.
We actually have not tested on the lifespan of the foil in Malaysia, but if you know Gardenia factory in Shah Alam, actually they are using our foil and it still remain good, and it's already about 15 to 20 years already.
I see. So that is something that is possible even beyond 20 years, right?
Yeah, if I'm referring to the Gardenia factory.
Okay. All right. Okay. So there's actually some interesting questions. It's a quite long one. Subjective study. These do not this study do not, okay, there's actually further comment, yeah. Maybe you can, share your viewpoints. Yeah. This is actually some of the opinion probably from the the audience. Okay, the comment is this study do not help to choosing the method for heat transmission through the roof space, which may comprise of the following: reduce reduction by using insulation on top of ceiling, or use roof tiles with good insulation. Number 2, reduce convection by venting airspace in the roof. Number 3, reduce solar heat absorption on top of roof tiles by reducing heat absorptivity, reducing color intensity. Yeah. So what is your comment on this statement? Yeah, I think there's some of the points that they highlight regards to your study lah. Yeah, yes.
Yes, because when we do this study, the time, we just wanted to test whether radiant barrier is really work or not. And different type of radiant barrier, for example, just I show whether it's woven type or foam type or bubble type. This time purely just want to test on the performance of radiant barrier. And I agree with you, reduce conductions by using insulation on top of the ceiling. Yes, this definitely will help. By calculation method, it definitely will help. I agree with you. And the convections by venting the airspace in roof, as I explained just now, yes, I also agree on this, but just is not evaluated in our tests. Yeah. And reduce solar heat absorptions on top of roof tiles. Maybe you are referring on the coating, if I'm not mistaken. Yeah, so this will help as well.
Yeah, perhaps this is some of the not addressed at the moment for this study, right? Yeah. Okay, then move for the next question. What is the estimate heat reduction after using aluminum foil? Yeah.
Okay, if based on our testing just now,
probably you can share in a percentage, is it? Yeah.
Let's look at the conclusions. There is, okay, comparing woven foil with bubble foil, there is a 0.5 degrees Celsius reductions as per our evaluations, field evaluations. Can you see from here?
Yes, okay. So we can, again, to answer the questions, can refer to this slide, yeah? And it's in terms of the first one is a percentage, and I believe the second one is the Celsius degree.
Degree Celsius, yes.
Okay. So we're looking at aluminum foil is referring to this. So typically it's like, it could be like 1.3% to even up to 4.4%. And with the range of like 0.5 to 1.7, right?
Yep.
Okay, all right. Okay, now we move to the next question. What is the RSI for metal roofing if only one layer of metal deck and not two layers?
You mean the RSI for the material itself or the RSI for the whole system? If for the material itself, RSI for metal roof, based on calculation method, usually it's 0. But this you have to clarify with the metal roof manufacturer. Okay. Then if for roofing system, then you will add in metal roof R value together with mass insulation R value. For example, like rock wool 50 mm or 50 mm 40 kg, it has 1.39 of the R value and another layer of foil. So that will be the system R value. So depending on which are you looking at, referring to.
Okay, yeah. So perhaps you can also contact Selena if you'd like to have a specific calculation method. Yeah, yes. Okay. So, yeah. So I think this is a very technical presentation here from Selena this morning. A lot of numbers. Yeah. Okay.
I hope it benefits to the audience.
Sure. Especially living in this tropic hot weather. Yeah. This knowledge is very beneficial. Yeah.
Thank you.
Yes. All right. Okay. So I think that is. Oh, this is the last. These are last questions, right? Yeah. So that is thinking that all the questions have been answered. Any more questions coming in? Okay. Yes. Thank you, Selena. I think we are coming to almost to the end of the session. Yeah.
Thank you, Regine. Thanks.
Yes. Yes. So, ladies and gentlemen. Oh, sorry. There's actually one more question before I end this session. Any tests on concrete flat roof? Yeah. The last questions. Yeah. Okay.
So far, no. So far,
Okay.
no. Yeah.
All right. Thank you, everyone. Ladies and gentlemen, finally, we have come to the end of the webinar session today. We'd like to thanks again to Selena for the very informative and technical talk today to the audience. Thank you for the precious time and your active participation and questions. Thank you for attention. We hope to see you again. Stay safe and healthy. Yes. Again, Malaysia GBC is a non-profit organization that promotes green building and sustainability. We're looking for more green-minded people like you to join us to grow the green economy. Please like our Facebook page, Malaysia Green Building Council. There will be also an online survey from the IGEM, so please take your time to reply in the survey link provided in the email. Yes. Thank you.
Thank you.